Back for the final assessment preparation video for Math 154. This is Unit 9C. We're going to be talking about exponential curves functions today. They generically have a shape that looks like this. If the base is positive and greater than 1, if the base is positive and between 0 and 1, they have a shape that looks roughly like this. So I'm going to say y equals a to the x. This is if a is greater than 1. This is if a is between 0 and 1, not included. Don't include 0 because 0 to any power would be 0. Don't include 1 because 1 to any power would be 1, and those would be horizontal lines and not these curves with these shapes. Okay. I say to any power, I mean any positive power. 0 would not be defined to the 0 power or to a negative power. 1 to the 0 power is also going to be 1. Don't be fooled by that. We're not trying to figure out what things are to the infinite power. Don't worry about that. General shape of an exponential growth function, that's this because it's growth, not decay, is going to be a rising curve, I think is what she calls it, a rising curve. You may call this the hockey stick graph if you've ever heard that by scientists, but it's going to be accelerating. It's going to be rising. It's going to be increasing at a faster and faster rate. So true or false, an exponential function grows or decays by the same amount per the same unit of time? No, that's false. That's what I just said. It's going to grow or decay faster as time goes on. True or false, exponential functions are useful for modeling lottery numbers? Nope. They're useful for modeling compounding interest. They're useful for modeling population growth. They're useful for modeling radioactive decay. They're even useful for modeling things like how long it takes for a cake to cool once it comes out of the oven, because there's something in science called Newton's law of cooling that's going to obey this exponential decay type thing. Yeah, that's what we'll talk about right now. True or false, after 80 years of population growing at 8% per year, will have grown by twice as many people as a population growing at the rate of 4% a year. That's false. Let's just show you that let's assume that my population is bacteria and that it doubles let's see, it's growing at 108%, right? So every year. So this is a model of y equals 108%. This is y equals, p doesn't really matter there. P was my original population. And this is 104%, like that. And for the sake of argument, ignore this here, and let's say the question then becomes, is after 80 years, is this number twice as much as that number? No, it's not. Prove that. Let's go ahead and put this over here. Something I wasn't convinced I was going to need to show you my calculator until just right now, but I need to show you my calculator. So yeah, I'm definitely going to need my calculator later. So to the 80th power, compare that number there to there's an even easier way to prove this. So if they're double, when I find their quotient, it should be 2, right? So let's see if this one, which they say that they imagine would be double that one. Okay, let's try this. What's 1.08 divided by 1.04 raised to the 80th power? If this is not exactly 2, then this one is not double that one. Okay, not exactly 2. All right. I hope that you knew that one conceptually without figuring all that out. But population of a town has an initial population of 62,828. It grows at a rate of 2.4 people per year. Create an exponential function in the form of Q. So I'm going to just say P of T is equal to initial population P naught 62,828 times growth rate is going to be 1.024. That's 124% is what its rate is, because you're going to have everybody from the year before plus another 2.4% to the T. So that's going to be my function. Now they want me to create a similar function here and make a table of values. This, and for the table of values, we're just going to use T equals 0, 1, 2, 3, 4, and 5. I don't have a lot of room to do that. So give me 1 second and I will put the whiteboard up where I have some room and can show you that. Actually, I changed my mind. I'm just going to do it in the calculator and have you guys write down the answers. So this is going to be 5. You have to be sure you type everything into the calculator right, including these parentheses here. And you're going to use the variable x instead of t. I used t because it was time. Remember, your calculator uses the variable x. We're going to only want limited values here. So I'm going to put my table settings to ask. And then I want year 0. That should correspond to my original year. 1, 2, 3, 4, and 5. And that's already rounding to the nearest whole person for me. But if I want to see that with more decimals, I can do that, but you don't get a fraction of a person. So go ahead and use these rounded values. Again, logically, you would round down here, because if you don't have that person yet, you don't have them. You don't have 6/10 of a person to round up. But I'm gonna just, I've already made that argument before, and I'm not going to get the calculator to obey different rules. So since I want you to use the calculator here, go ahead and have the calculator round to the nearest person and go ahead and use those numbers, which are going to match the numbers that you have down here for your answers. See that? The population of town with an initial population of 56,112 grows at a rate of 3.3%. So want you to make a graph of that. Well, okay, I'm going to do that in Desmos because I don't trust my calculator to make a good graph of that you're going to be able to see. Just a second here. I want 56112 times and 1.033 raised to the x. I want this to be y equals, and it's already there. I just can't see it, so I'm gonna zoom out until I can see it. Oh, there it is. See it? So, and you can pick some points on here that you can graph, but you know that it's not going to cross the axis until when x is 0, this is going to be 56,112. So you're probably not even going to get to the y-intercept. You're probably going to need to graph it. And this part down here, it's mostly negative. Zoom in, and or we can just, you know what, we can also come up here. If we know that we've got that particular value that we want on the graph, let's go ahead and do that and show you why I was saying what I was saying, because it's already turned so much by that point. 56,112. If I want to zoom in here to the point where I'm going to be able to see that y-intercept, what was that, 112? Keep going here for a second or two. This is why I said I didn't want to do any of this on the calculator, because I can't just scroll my mouse like this. There's that point that I want, right? That's my important point. So let's zoom in. Let's get close to that point. As close as I can get. See if I can start to see some shape of the curve other than it looking like it just goes straight up. You gonna see anything? Nope, I'm not. I'm not gonna see any detail in the curve because it's rising so fast there. So to get the shape of the curve, probably not gonna be able to even include that y-intercept point. I am going to want to just go ahead and, like I said before, zoom out until I can see, ooh, it turns. See that? And then focus in more on this point down here where it turns. You're not going to be able to find out where that turning point is, but this is probably a better image. Even though it represents population, you're not going to get negative time and things like that. This is probably the better part of the graph to zoom in on here. All right. They really just stretched out the scale. Do you see that? That's how they got away with it. And their number 7 is they used numbers that are 1, 2, 3, 4, 5 here, and they went by thousands on their scale. So if I do the same thing here and say I want to adjust my x-axis to go from 0 to 5 step by ones. Let's step by tenths. I don't even, yeah, step by ones. And then my y-axis, I want to go from, what was that, 30,000 to 90,000. I want to step by 10,000. Now see, that's how they got that, but this is deceptive because it's stretched out and this looks almost linear. And I assure you that the graph is not linear, it's exponential. So be careful when you see things that are way out of square like this, that someone's not trying to trick you and zoom in on such a small part of the graph to make it look like something that it's not. It should be rising very quickly here. So we're seeing a change of what was this? This was a 52,000 something up to, so this is not quite 70,000. It's rising, like, let's say 6,000 people over those 5 years. Yeah, it's a lot. Okay. Now we're going to talk about what to do with a percent decrease instead. It's decreasing. So that means R is going to be negative. Okay, so what that means to me. So we start off with 72, 526. We need to multiply it times. And now we're going to take that 100% and subtract 3.5% from it. So that's going to give us a 96.5%. But we don't want to write that as a percent. We want this .965 like that. This is to the t, not t. This is raised to the t. Raised to the t power. And then they want us to do something similar here. We write the equation. This is 69,064 decreasing at a rate of 2.8%. So this is going to be times. So that gives me 97.2. And this is raised to the t. And they want the chart for the first 5 years again. Let's go ahead back to the calculator, show you y equals, and this is going to be 6, 9, 0.064 times 0.972 raised to the t. And I'm going to go to that same table for the first 5 years, and we're going to see this decreasing. Right? Yes, decreasing year over year. See that? Start off at 69,000, then it's at 67,000, 65,000, so on and so forth. So you can copy those numbers down. Again, I'm not going to worry about the fact that it's if you whole people or not and rounding rules. Let someone else talk to you about that. Maybe you'll talk about that in statistics. I don't know if you'll talk about the greatest integer function there, but you would have talked about that in pre-calculus before you took statistics. So I'm just introducing you to the idea of, I'll draw it here since we never talked about it. There's this idea of a step function, and it starts and it looks like this, and then it steps like this. I don't think we ever talked about this function. It's called the greatest integer function. Your calculator does it. It as INTX, and that these things are all the same width, and they're all spaced by the same height here, like that, and they look kind of like a staircase, but it jumps every so often. And that's what that's what happens when people are born, right? You don't have a person, and then you have a person, and then you have another person, and so on, and you don't have parts of a person. So I was talking about this again. We want you to think critically with this class, think logically, and sometimes you either have something or you don't have something, and that you need to, you don't really have a car if you have a car with 3 wheels that you can't drive, right? Unless you have all the parts there, you don't have the next car. So let's just answer this last question here. Population, town has an initial population of 52,576 and is decreasing at a rate of 4%. That means that I have a 96% rate here. Then it wants you to make a graph. I'll show you how to do that in the calculator. We're going to have to do the same thing where we kind of stretch this out like we did before. So y equals and 52,576 and times a 0.96 raised to the x. I'm going to play with my window because this is going to be the tallest that I want it to get. So I'm going to say that I want 60,000 up here at the top, and I want to go down to maybe maybe 0. Let's go 0 here, and it's not going to get all the way down to 0, and let's give it 15 years. Okay, let's see what that looks like. Let's go by 10,000s on the left-hand side. So window, and go from 0 to 15, and they're going to go by ones. And then I'm going to go 0 to 60,000, and I'm going to go by 10,000s there, and we're going to graph this. There we go. You see, you can kind of, because I went out further here, kind of see more of that shape of it bending. If I went out to 25 years instead, you'd see even more of it. Okay. If I went out to 100 years, you'd see even more of it. See that? But you don't want to make 100 tick marks here, do you? So pick something that is, reasonable for you, how much you're going to graph. Maybe if you go to 50 years, maybe you want to scale this to tens so that you'll still only get 5 tick marks, but maybe you get more of the shape. You see that? So it won't necessarily look linear that way, but you can say, well, this is 10, 20, 30, 40, 50, and I get more of that exponential curve shape. I would try and make sure that you get the proper shape of the graph, not necessarily that you get small numbers, because that's what we have calculators for. Because you don't want someone to assume that you're showing them a line because you zoomed in too much, when clearly this is a exponential growth or decay curve. All right, that's it for this class. It's been great working with you guys, and look forward to seeing anybody for final exam review questions that has any either one-on-one tutoring in Math Central Plus, or if you have an embedded tutor in your class, go ahead and see them for assistance as well. Have a great exam, and hope you all do well in your class. Bye now.